Well, so today, inshallah, we will start a new algorithm, which is also a population-based algorithm. It is some kind of genetic algorithm in that direction, but little bit different from genetic algorithm. And as we mentioned earlier, all these techniques, they are different in terms of the operations that you implementing to generate offspring from the parents. Some of them use mutation, some of them use only crossover, some of them use different operators to generate the children out of the parents. As we will see in today's algorithm, which is evolutionary programming, and later we will see also for the swarm-based techniques and also physics-based techniques. So before starting, I would like to give you some kind of brief tutorial about how to use the genetic algorithm in Matlab. As per your request, some of you, they request just brief tutorial. Definitely you can enjoy it, and you can go and train yourself. You can entertain it. What we will do here, very simple example and how to use it, how to use Matlab to solve the genetic algorithm problem. And I think it is just plug and play. It is not previously previous semesters I usually asked the students to develop a code for genetic algorithm and the other techniques also. The idea behind this, you can develop, you can access the code. If you have any idea, new idea or innovative idea, you can implement it. If you can come up with hybrid technique, you can implement it if you develop the code by yourself. But let us due to the time and this environment, and usually the communication or face-to-face, I can check the codes for the students and we can debug it. But now the situation is a little bit different, and I will ask you to use the toolbox of Matlab to do it. So, for example, if we need to, I don't know whether I can write here. Oh, this is not possible. If we can. Okay, and let me ask you if we have a very simple function, y equal to x minus 3 square, and we need to minimize this function. What do you think the minimum value or the optimal solution? Any solution? Any answer?
Doctor, sorry, what is the function again?
Y equal to x minus 3 square.
Three, Doctor. 3.
and minimum is 3. Yes, and the optimal value or the objective function at that time equal to what? Equal to 0. This is the objective. This is the function. So the solution, the optimal solution is 3, and the objective function corresponding to this is 0. So let us see how to implement it using genetic algorithm. Actually, are you seeing the cursor here, a mouse?
Yes, Doctor.
Are you seeing the mouse? Okay. So let us start a new script here, and we define the function. So we can write here a function, and we need to name this function. We need a unique name in order to not to interfere with the built-in function on Matlab itself. So let us take, for example, I think Abid is not there in Matlab. Definitely. Let us say y here. Y is the function equal to Abidu of x, for example. Y is the output and x is the input. And the function is defined as y equal to x minus 3 squared. This is the function. Okay, this is the function. You have here two options in order to solve using the genetic algorithm. You can use the command window here, or you can use the graphical user interface. Let us see if you use just the command line here. So there is a function in Matlab called GA. So GA, the genetic algorithm. So you will open here, bracket, and then you can see here these are the options of GA. If you want to go here, this is the function name. You have to set here the function name and number of variables. And in this example, we have only one variable, x. So n bars here equal to 1. If you have equality and inequality constraints, طبعا الديفولت, let us say in the default optimization here is the minimization problem. So default is minimization problem, and the default of the inequality constraint is less than or equal. So even if it is greater than, you can of course multiply by minus sign both sides to convert to less than. So this is the function, and this is the variables, number of variables. And if you have inequality constraints, if you have, for example, x must be less than or equal 10. If you have two variables here, x1 and x2, so you can write them in matrix form, coefficient of x's, and this is the absolute vector here. So A and B can be written. If you have equality constraint, you can use also equality constraint similar. You have مثلا 3 equality constraints in the variables. So you have here a matrix of 3 rows, and whatever number of variables. It could be 2, could be 3, could be 4, whatever. So this is the number of rows here is equal to the number of equality constraints. And this is of course, the absolute vector. If you want to limit your search, this is the lower bound, and this is the upper bound of the variable. So you can limit your search to lower limit and upper limit, as we will see. Of course, you can enjoy the others later. So let us start with very simple one. Let us define this is the function is abidu. So this is abidu, and the number of variables 1. So this is what we have here, and then okay, what is this create function? Oh, and I didn't save it.
Yeah.
I didn't save it. So let me save, and since this is the function, and I will need to save the file, the name of the function. So this is abidu. Okay, now we can go and do it. So as you can see here, the optimization terminated, and the average change in the thickness is 3. So this is the variable here. So this is what we expect actually. Am I right? So this is what we expect. If you, of course, as you can see here, 3.0025. Okay, or if you want to the function itself y, I think you can write here xy. And let us see. So the function value, of course, the optimal value should be 0. But this is very, very, very small طبعا, of course. The genetic algorithm approaches 3, but as you can see here, it is very close to 3. Of course, if you limit the bounds, طبعا انت الbounds here are open, or default values, which is from -10 to 10. This is the default. But if you want to limit the search, if you want to, you can get from this انه يعني the promising solution is around 3. So let us limit ourselves. Let us put some bounds, upper and lower bound here. So what we will do is we don't have the inequality constraint. We don't have equality constraint. Let us assume we don't have any equality constraints, and we will set here the lower bound. Let us put it equal to 2, for example, and the upper bound, let us put it 4. Hopefully the solution generated here is very close to 3, closer than this one. But if you can see here, the solution here is 3.0025. When we run a genetic algorithm again, it gives us another solution, 2.99. طبعا لان everything is random, فانت you create يعني another sequence of random solutions, and this is why we have. But of course, the robustness of the technique can be validated. If you calculate the average, the maximum, the minimum solution, you can see these solutions are very, very close to each other. So let us start with this. Now we narrow. We are searching in narrow range now. We limit the lower bound and the upper bound of the solution. Hopefully we can get better solution closer to 3. And this is exactly comes here equal to 3, the solution, and the function value is approximately 0. So this is the case. It's very simple, very straightforward. If, for example, you have two variables. Let us say another problem. Let us say two variables. We have here same definition. We have here x1 equal minus 3 equal to 0, and we have also another term here, which is v plus, let us say, x of 2 minus, for example, 6 square. So we have here two variables, and this is the function. Let us save it here. So what do you think the solution of the function here? What is the solution now? Minimum value. The minimum value to be 0, and this happens when x1 equal to what and x2 equal to what?
3 and 6.
3 and
3 and
6.
6. So the solution is known in advance. So let us go here and let us solve it. Generally, we have here two variables. So we can open the search, or we take the default range. There is a default, and I would like you to go over that's what we will, just in a few minutes we will discuss it. But this is for two variables problem, and let us see here. You can have the solution is 2.988 and 6.04, and this is why. So if we go back to this one and put the limits, lower limit and the upper limit. For the first variable, for x1 we have 2, and for x2 we can put the limit here equal to lower limit. Now we are talking about lower limit. What do you think?
5.
Let us put it 5. And then these are the lower bound of the x1 and x2. The upper bound, we put 4 for x1, and we put, let us put like 7 in x2. So this is the case now, and we can run GA to see this. What is this? Oh, now here two variables. You can see here number of variables. We need to adjust it. We didn't adjust the number of variables. Now we have number of variables equal to 2. Okay. So this is the solution now. You can see the solution is exactly at 3 and 6, and this is the objective function is approximately 0. So this is the way it is done in terms of the command line. Of course, you can create, a main, main program, and then you can call GA directly if you have, for example, this one. Let us say to the main here, and you can create this, and you save it as a main program. So this is, of course, needed, and then you can run the main program. So it will call the function and will solve. So again, it gives us, of course, this value is different a little bit. And the resolution of these numbers are for decimal, but if you expand it, but again, it gives you for 3 and 6, and this is very, very small value. So this is the main program. You can call the function and you can run it. So this is the way. The other way to do it is to for graphical user interface, you can use the optimal tool, optim tool. And then you can run it, and then you continue. It open like this graphical user interface. Do you see it?
Yes, Doctor.
Yes, we see it, Doctor.
So the first one here, you select the optimization technique that you need to implement. We have here genetic algorithm, so let us choose genetic algorithm, and let us define the function here. This is the function name. Number of variables is 2, the last version. If you have equality constraints and inequality constraints. طيب, let us see for this example, specific example, without constraints, the solution is 3 and 6. Am I right?
Yes, Doctor.
Yes, Doctor.
طيب, if we add a constraint here, إنه x1 plus x2 should be less than or equal 8. Now we know that the solution is 9, but we force x1 plus x2 to be equal or less than 8. Is it clear? So
Yes.
in that case, we can have the solution equal to 2.5
And 6.5.
and 5.5. Am I right?
Yes.
So we can have here matrix A is coefficient of x1 and the coefficient of x2. But of course, then we have only one constraint, and B equal to like 8. So we have now x1 plus x2 less than or equal 8. So this is inequality. This is inequality constraints. Okay, so let us, of course, you can put the bounds, or let us open the bounds for the time being. But the bounds are similar to what we have in the command line. You can put it equal to a lower bound, and then the upper bound. You have two variables here, so you can do it as we did before. So we can start here. If we start here, let us see what is going on. After 97 iteration, we have the objective function value comes up to 0.4999, يعني 0.5. طبعا keep in your mind انه ان احنا we limit, we will not reach to 0 now. And with this constraints, we will not reach to 3 and 6. So this objective function, we have a certain objective function, and this is the solution. For the variable 1, we have 2.49, and for variable 2, we have 5.507. So, you know, this is the summation equal to 8 or less than 8. So this is why we reach to this solution. Of course, you can, if you have another constraints, you can also write, now A becomes a matrix. You can have it as such. I don't want to go in details, and you definitely you have good experience on this, and definitely you can go to the toolbox and see what's going on there. So this is the graphical user interface here for genetic algorithm, and as you can see, it's very straightforward, and you can see here some of the variables that you need to either you keep it as default or you specify it. And هنا user default initial population. So you can have the initial population here. You cannot. In some cases, you don't need to start from scratch randomly, but you need from the last solution, for example. So you have previous solution, and you are going around this solution. So you don't need to start from scratch. You can see here population type, population size. You can specify initial range, selection function, and so on, stochastic uniform. يعني a lot of يعني here crossover fraction and elite count if you implement elite or elitism. You can have here nonlinear constraint algorithm, and there are several defaults. As we mentioned, you can play with it, or you can use the default if it is if it is okay with you. So this is the graphical user interface, and definitely I posted this global optimization toolbox in Blackboard today. So you can see here the using the genetic algorithm, you can read and you can entertain these examples here. You can have such example, and you are of course definitely for optimization we have some standard functions which is difficult functions for any technique to test against, and if the technique is able to reach to the optimal solution which is known, so you can this is the graphical interface, and of course you can go and you can see here the several examples. Defaults, crossover, mutation, and so on. So you can implement, of course, any of these options that you can use. This is also posted on the Blackboard, so you can read it and you can learn more. So if you have any question, this is just a quick tutorial. I believe these such things is you can learn it by yourself if you dedicate 1 hour to go through these examples. You can get it. Do you have any question? Yusuf. Yusuf. Yusuf Al-Hussein.
Hello.
Any question?
No, bus.
Clear?
Yes.
Okay, great. So let us close this one. Let us close this one. Let us close also Matlab. And then we go to this one.
Sorry, Doctor, for interruption. I have a small
Yes.
question regarding this toolbox.
Your
Is it
voice
just
is
especially for... Sorry, Doctor. Now, is it,
okay. Yeah, it's okay. Go.
this toolbox is especially for genetic algorithm?
It's not for genetic algorithm. This is for different optimization techniques. You can have mixed integer linear programming. You can have if you read it here, we can go to lectures, and then we can go to Matlab toolboxes. You have here this one. You can see here the techniques available. Of course, you can use another technique to just to compare with the genetic algorithm. You can have here. This is just a tutorial for how to. The techniques, في direct search technique, and you have a genetic algorithm. You can use also particle swarm, as we will see later on. You can have simulated annealing. Oh, it's still here also, simulated annealing. And you have multi-objective optimization. Then you have different techniques here that you can implement. Okay.
Okay, thank you.
Of course, from the graphical interface, you can have several options as we show you for the drop-down menu that we have in graphical user interface at the beginning. You select one of these techniques to solve the problem. Okay. Did you still remember it?
Yes.
Hmm? Tool. Okay, continue. You can hear constrained nonlinear optimization, min-max optimization, unconstrained, nonlinear, single variable, and so on. And you have different also functions here. So you will see here the other functions, simulated annealing, as you can see here, and also other constrained linear list. And there are several optimization techniques in this toolbox. So you can just use the one that you need. So for example, genetic algorithm, as we are discussing right now. Okay. Okay, so let us start a new technique, which is more or less from the family of genetic algorithm, and also it is, the principle of operation here is survival of the fittest. So the better solutions will continue and will be able to produce children. The others will not survive. So this is called the evolutionary programming. And what we will see here is, we have here Muhammad Tahir, please.
Yeah, salam alaikum.
Salam wa barakatuh.
Just these slides are not posted.
Which slide?
The one you are sharing now.
It is posted, yeah.
The posted is a paper.
Paper? You mean
Yes.
text, yeah.
Yes.
Yeah, what text? Yes. Yeah, the text here is the same as the text posted.
Okay.
And same. It's
Okay.
same.
Thank you.
The material is the same. Evolutionary programming algorithm. We'll see the algorithm after discussing the advantage and so on. We will see how to proceed with this evolutionary programming algorithm. Initialization step, and which is similar to genetic algorithm. We will not add much here. You start randomly, select randomly number of solutions, and then here we have a mutation operator done, and then we do some statistics in order to see which one is better, and so on, minimum, maximum objective functions that we have. And then we update the population. And then we do tournament selection, and then we select, and then we have a stopping criteria. So these are the steps for the algorithm. Compared to genetic algorithm, what is missing? What's missing here?
Crossover.
Crossover is missing, yes. There is no crossover here. We have only mutation. Selection the same. Okay. So also you can implement elitism. Mutation is done here a little bit different than genetic algorithm. It is a unique operator here. The mutation is not similar to genetic algorithm. But the initialization is the same. The statistics is just statistics. When you have solutions, you can calculate the objective function and you can get the minimum, J minimum, minimum objective, you can get the J maximum. Of course, this would be the best one, assuming this is a minimization problem. This is would be best one and this is the worst one. You can get also J average, average objective. You can use it later on in the stopping criteria. And then you can do some kind of tournament similar to what we have in genetic algorithm. You select randomly and you compare, and then you can, give a weight here. A little bit different than genetic algorithm, but the same concept. You compare and then here you give a weight. When you compare and this solution is the winner, then you increase its weight and so on. So you do some kind of selection and the stopping criteria similar to what we have in genetic algorithm. So evolutionary programming is the exploratory search. The first 2-3 slides here is just general, similar to genetic algorithm in terms of the structure of the technique, in terms of the advantage of the technique also compared to traditional optimization. It is the same advantage as genetic algorithm. So these slides are a little bit general. Evolutionary programming is exploratory not only for evolutionary programming. If we have another technique, we can repeat the same. Evolutionary programming is the search optimization procedure that was devised on the principle of natural evolution and the population genetics. So same principle. Unlike conventional optimization, EB works with a population, a number of solutions here. And when that each point here, number of a population of points or solutions, and each point represents a different potential solution of the problem. For each generation, all the population points are evaluated based on a certain objective function, which is a general point. The fittest points have more chances for evolving with the next generation. This is usually the case also. Nothing new. The advantage of EB, it is the same as advantage of G8 or this family of the techniques. The advantage of EB over other traditional optimization techniques can be summarized as follows. Do you still remember what are the advantage of GA over the traditional optimization? What do you think? What do you think?
It doesn't have the limitation of the classical optimization method, which is calling for local optimization.
One, escaping from local. Right? This is your point. Second,
model free.
model free. What do you need? What do you mean by model free?
The like the neural network can be modeled
الصوت يعني your voice is cannot hear anything from you. طيب any other
Is this better now, Doctor?
okay.
Yeah, the model for the neural network can be modified easily to obtain the desired output.
Sorry again.
The model for example, the model for the neural network, does not play a critical role in relation with the input to obtain the desired output.
This is the neural network.
Yes.
It's not a genetic algorithm, and we are now comparing the genetic algorithm with the conventional optimization. Conventional optimization, the gradient descent. Your voice is a problem.
Yeah, I think I have a problem with the mic.
Model free can be okay with neural network and the fuzzy logic. Now here for GA, definitely if you want to calculate the objective function J, you have to have the model of the system in order to calculate the objective function. Objective function is the function of the sum of the variables there. So you need the system model. Unless you do system identification, this is another story. So model free doesn't fit well here yet. Let us say. Escaping from local optima, this is one. Second, Barak, you want to
Can
say?
be for can it solve the complexity of the objective function?
Yes, this is one. No restriction imposed on objective function. You don't need the objective function to be differentiable as we have in gradient descent method. You have to have it differentiable. You don't need this objective function to be linear, to be continuous, to be smooth. You can have any objective function that you want to calculate. Any performance index you can define with no restriction. Okay, so this is very important feature of genetic algorithm over the conventional optimization. What else?
Probability base.
These are a stochastic search. Stochastic search. So it is not deterministic. So it is more robust than the conventional optimization. What else?
Does parallelism have any role here? Genetic
Yes.
revolutionary programming.
Yes, it is population-based technique. Genetic algorithm, population-based. You are dealing with a number of solutions at each generation. So this, you have some kind of parallelism. So you don't have only one solution and you follow, but you are working with 10 solution, 50 solution, 100 solutions at the same time in each generation. So you have some kind of parallelism. And this will make you less susceptible to local optima. If you have a number of solutions, so most likely you will escape from the local optima here. Okay, so these are some of the advantages of GA, and also some of the advantage of the evolutionary programming. Well, same structure and same family. And this family has such advantages over conventional optimization. Not only for evolutionary programming, we have it also for differential evolution, for particle swarm, for others. So EB or GA or whatever, search the problem space using a population of trials representing possible solutions to the problem, not a single point. So it has some implicit parallelism. This implicit parallelism property ensures EB to be less susceptible to getting trapped in local minima, and therefore EB can reach to global or near global optimal solution. As we see here in the Matlab very simple problems, you can see that the solution approaches the global optimal solution. And EB, evolution programming or genetic algorithm uses performance index, or performance index or objective function information to guide the search in the problem space. Therefore, EB can easily deal with the non-smooth, non-continuous, non-differentiable objective function. There is no restriction on the objective function. So also, this property relieves EB of assumptions and approximations which are often required by traditional optimization methods or many practical optimization problems. EB uses probabilistic transition rules to make decisions, not deterministic rules. And you have crossover probability, you have mutation probability, you have randomness and getting this and that. So this makes the search robust. And EB is a kind of stochastic optimization algorithm that can search a complicated and uncertain area to find the global optima. EB makes, this feature makes EB more flexible and robust than conventional methods. So let us see the algorithm step by step. Let us see the algorithm. But then, again, we need to emphasize that these advantages are for the family of population-based techniques. Okay. EB here is the population size. Let us say population size is 2n candidate. We assume that population size is 2n. And if you have مثلا population size or the whole population is مثلا, for example, 50 solutions. This 50 solution represent 2n. So here n equal to 25. And n here is the half of the population. Each candidate solution, of course, represent an m-dimensional real valued vector. And this m is the number of optimized parameters. And you have chromosomes like in our problem, in our control problem, you have 3 parameters, K, T1, and T2. So this is the chromosome here, real valued parameters here, and these are m here equal to 3. For this specific problem, you have 3 optimized parameters, so m equal to 3. This is the dimension of the solution. And the EB algorithm can be described in the following steps. Step number 1, similar to genetic algorithm, we have to start with the initial population, and this initial population is selected randomly over the search space. What is the search space? Search space is defined as the range of the optimized parameters. Yani for example, K, you have K ranges between 1 and 100, for example. So this is the range of K. For T1, for example, you put it 0.1 to 1. And for T2, you have the range of 0.01 to 0.2, for example. So this is the search space is governed by 1 and 100 in this. You have here this population, this and this. So this is the range of K dimension, and this is the T1 dimension between 0.1 here to 1, and this is for T2 dimension. You have this one is 0.01 and this is 0.2. So three-dimensional as such, each solution. So initialization, you start randomly within this range, and definitely you know how to start randomly. You know, this is similar to genetic algorithm, nothing new. Set a generation counter K equal to 0. This is the initial generation, and generate randomly an N trial. We generate randomly here half of the population. N trial, half of the population. If you set the population size equal to 50, you generate only half of the population randomly. This solution, or this random solution that you will see, you will generate here 25, N here equal to 25. And each solution is, have 3 parameters here, each solution. And these parameters are, calculated or generated with these bounds here. So you can B1, for example, which is the K, and minimum, maximum, you generate a random number, and then you get the value of K, the value of T1, the value of T2. So this is the first solution, and then you, of course, this is definitely the same as genetic algorithm, so you can easily do it. Any question? Initialization step. You select randomly half of the population, and this half of the population, you will implement mutation step to create the other half of the population. These initial trial solutions constitute the parent population and the initial generation equal to 0. Each individual in this initial population is evaluated using the objective function J. Of course, once you create the solution, you can calculate the objective function associated with it, and you can search for the minimum value of the objective function, or you can say the best solution, and also you can set this solution as the best solution. Keep in your mind, in our optimization process, we need at the end, the ultimate goal is to find the best solution. So we set the best solution here with the minimum objective, that this is assuming it is minimization problem without loss of generality. So this is the best solution, and the objective equal to J best, J minimum equal to J best, and X minimum equal to X best. And this best solution will be updated whenever you have new solutions. You can update and to compare. If you are able to find a better value than the value here, then you can, update the best solution. Okay, so we need to fill the population. We still have half of the population needs to be filled. Each parent xi. Each solution that you generate randomly out of 25 produces one offspring. يعني each solution you create one child. يعني from the solution, from only one solution you create one child. One solution, one child. As we mentioned, there is no crossover here. So you are working on one solution, and from this solution you create a new child here. How to create this new child? This is xi and this is xn plus I. Yani the first solution will create x26. Assume this is 25, n equal to 25. You create this randomly, created randomly, and this solution x1 will give us one child here, which is x26. And x2 will give you x27, and so on. So each solution will create a new offspring. How? We will see. Perturb each optimized parameter. You go for each. This solution is K, let us say T1, T2. This is the solution X1. We need to create a child out of this solution. So perturb each optimized parameter, which is K or T1 or T2, by the Gaussian random variable n of 0 at the average, and this is the standard deviation or variance. The standard deviation sigma j specifies the range of the optimized parameter perturbation in the offspring. The sigma j is given according to the following equation. So the idea here, and you have this solution. This solution, for example, is 8.5, 0.7, and 0.2, for example. So you will take this number and you will move around this number, but not uniformly, but Gaussian distribution. And this is 8.5. And I can move around 8.5 with this probability. So you can, you are going around the 8.5 mainly. You can go here with very low probability. You can go very far from 8.5 with very low probability. So around the 8.5, you will move, you will perturb the solution. Around 0.7, you will find a value which is near to 0.7 with this distribution, or 0.2, okay? So for each optimized parameter, you calculate the standard deviation. And this is the standard deviation for parameter 1 equal to beta. This is a constant. Let us say we'll talk about it now. This is the objective function of x1, which is known definitely. The J maximum and maximum value among the objectives of the 25 solution that you already generate, you can have it. Definitely, you can find it. And this is the objective function of the current solution. And this is the range of the parameter. If you are talking about K, so you will take 101. If you are talking about T1, so of course you can handle this. So what is the idea here? The idea here is this beta is a value between 0 and 1. Let us, to understand this, let us assume the extreme cases. Let us assume the extreme cases. Assume the beta is constant, 0.2, 0.3, whatever. What are the extreme cases? If this is the minimum, or if this is the maximum, if this is the best solution, or if this is the worst solution. If this is the best solution, if this is the best solution based on objective function, do you want to go far from these values, or you want to be very close to this one?
Should be very close.
Okay, you are right. Definitely you want to be very close if this is the best solution, if this gives you J minimum. But if this is the maximum, gives you J maximum, so that means this is the worst solution. So what do you want? You want to go far from this solution, right? So you need to have standard deviation, high standard deviation or large standard deviation. But for J minimum, you need the standard deviation to be very, very low in order to keep the perturbation very close to the original value. So look at this Ji over J max. If this is the minimum, this gives you minimum value of, these are constants, beta maximum, minimum, this is constant for a specific parameter. So if this is the minimum, if this is the best solution, so sigma will be very, very low. If this is the maximum, this becomes almost 1, and J becomes large. Is it clear?
Excuse me, doctor.
Yes, please.
I think this is dependent on the initial population. If the initial population have a good objective function, then it will be okay. But if it is, I think it might be trapped in the local minima or local maxima again.
Now we start randomly.
Yes.
We start randomly. We have now only 25 solutions. Okay. In these 25 solutions, you calculate J1 up to J25. You calculate it.
Yes.
Right? You can do some statistics here. You can get the J minimum and J maximum. Definitely, for the solution corresponding to J minimum, this is the best solution that we have right now. Well, maximum is the worst solution that we have right now.
Yes.
Sigma, by the way, sigma is not fixed throughout the search. Sigma will be different from generation to generation.
Okay.
When you have here J of Xi, when you are talking about the second generation, you have different solutions, you have different J, you have different J max. Okay?
Yeah, okay.
So X1 will create X25, 26, n plus 1, X2, xn plus 2, 27, and so on. And these are the standard deviation for each parameter. We will calculate it. This is for sigma k, sigma T1, sigma T2. Okay?
Yes.
Okay, so this is the standard. This is the standard deviation, and then you need to generate a random number between with the average value equal to 0 and the standard variance equal to sigma square. So as we mentioned here, this is the Gaussian distribution. So any deviation or the random number here will be added to 8.5. It could be positive, it could be negative. So this is the average here is 0. So it could be positive, could be negative. So you add it to 8.5, so you go this way or you go this way. So you move around the parameters, but with the Gaussian distribution. Beta is a scaling factor. Just you can put it whatever you can make it intelligently. You can say, you know, this is the range of the variable. This is the range of the variable. Okay, B max minus B minimum. So if we take this range from B max to B minimum, B minimum to B max, let us assume that this range will be divided, for example, to 8 intervals or 10 intervals. 10 intervals. Yani what we can do, we can allow maximum 10% deviation. Either you go this way 10% or you go this way 10%. You can divide this range over 10, مثلا, for example. You can say in the beta equal to B max, B J max minus B J minimum over 10. What does it mean? And no, if this is the maximum, if this is the worst solution, so J equal to J max, so this becomes 1. And if you have this equal to 0.1 of this value, so sigma equal to, this will be 0.1 times this. So 0.1 times 100, مثلا الرينج كله is 100. Assume this is 100 minus 1, and almost 100. So beta is calculated here equal to 0.1. So you can allow for plus minus 10 out of this solution. This is the maximum. But definitely, if you have any value different than maximum, you will get just close to this value. You can do this for setting the beta. You can allow for 10 intervals or 8 intervals. You can make it even adaptive if you want. At the beginning of the search, similar to what we have in genetic algorithm with the non-uniform mutation, at the beginning we have, we can allow for big step or big change. And while we are moving forward and approaching the global solution, then we can minimize the change of the parameter. So we can do the same, but anyway, you can put it constant. You can, relate it to the intervals here that you want to move forward. Beta is the scaling factor, and J of xi is the objective function of the trial solution that you generate here randomly, which is xi. Is it clear? Any question?
Doctor.
Yes.
Just a quick question. Now, when we divide the interval into, for example, 10 intervals here.
Yeah.
Are we talking about that we will be selecting one population and moving around that within that interval?
No, it's not population. Here,
okay.
You assume that you select a 10 interval, or you divide your range for K or T1 or T2 by 10 interval, right? For K,
yes,
it is 100 range over 10, so beta equal to 0.1. Okay? Is it clear? So what is the implication of this? What is the implication of this? And if you have a value here equal to 8.5, how far you can allow for this to change? How far? 10% of the range. 10% of the range. And this can go up to 18, or can go down to what? خالد سليمان ولا فوزان اللي معايا؟ فوزان. خالد I will come back to you. الفوزان.
راح الصوت يا دكتور.
الفوزان.
Yes.
If this is the value of k and you allow here beta equal to 0.1, okay? So the maximum step, maximum change for this k will be 10% of the range. 10% of the range. And the range can 100.
Yeah.
10% is 10.
Yeah.
So you can go up to 18.5 or you can go down to what? This is my question.
Minus something, minus 1.
Minus 1.8, minus 1.5.
1.5 تقريبا, yeah.
But as we mentioned last class, and we have to stick with the feasible solutions. So if k equal to 1, this is the minimum, so you have to stop here. And you don't allow this parameter to go to minus 1.5. Minus 1.5 is unfeasible.
Yeah.
Am I right?
Yes, clear.
So when you implement this, you have to check the bounds of each parameter, and you can fix the parameter value as its bound, or its violated bound, okay, or violated limit. So this is the implication of beta, Fawzan. Is it clear?
Yeah, okay. Yeah, yes.
Khalid Sulaiman? Khalid.
Yes, sir, I just want to clarify one thing, please. Now, x1 is going to produce x26 in this particular example. So x26 in this case, it will have 3 parameters. Now, for this example, the new k in x26 will be calculated by adding the Gaussian random variable to 8.5, right?
And you assume here in the average is 0.
Yes.
And you calculate the standard deviation.
Okay.
And assume that the standard deviation here come up with, for example, you have this a fraction equal to, for example, 0.1, and this is equal to 0.1 also, and this is equal to 0.1, so 0.1, 0.01, يعني 1 على 100, 1 over 100, and the range here is 100, so you end up with sigma equal to 1 or 2, whatever يعني. Is it clear? And you end up with here with the sigma equal to 1 or 2 or 3 or whatever. So you generate a Gaussian, a random number with the Gaussian distribution of 0 and 4, or 0 and 2, 0 and 4 variance. So what does it mean? It means no, you have this distribution around the 0. This is 4 sigma, and this is minus 4 sigma. This becomes 0, and you generate, and this is minus 4 and 4. So if sigma equal to 1, so you are going from minus 4 to 4. You select any random number here. Okay, so assume that you select 2. So this is 2. So this 2 will go with, this is the random number that you select. So this 2 will be added to 8.5. This is the change in k. If you select it minus 3, this will be less probability. You select minus 3 here. So this minus 3 will be added to, so this is the perturbation. This is a perturbation of the parameter.
Yes, and that's my new K, doctor. That is the K that represents
Yes.
26.
Now,
okay.
This is the K of x26 will be 8.5 plus this random number. For example, -3 مثلا. So it becomes 5.5. And this will be repeated for T1 and T2. Okay?
Yes, another question, if you allow me, doctor.
Yeah,
Would it,
go ahead.
Thank you very much, doctor. Would it be different if we used uniform distribution rather than Gaussian?
You can use definitely the uniform distribution. You can generate between 0 and 1, and you can definitely you can do it. But this Gaussian distribution means what? Means, this is like an adaptive mutation. And if the solution is good, we don't want to go far from it. If the solution is bad, then this sigma will be high. So this would be the distribution. If sigma is high, assume that sigma here, when we calculate sigma here, assume that this is becomes 1. And j over j becomes 1. This is the worst solution that we have. So in this case, sigma becomes 10. 0.1 multiplied by 100 here range. So this becomes 10. So that means you are going from -40 here, or 40, to 40, -40. So you allow, the random number to be very, very far from the original value. When you create here 30, for example, you add this 30 to 8.5. So you go far from the solution, from this bad solution. So this is some kind of smart thing. It's better to have it Gaussian and some kind of adaptive. Is it clear?
It is very clear, doctor. But wouldn't beta help? If I don't partition beta, would I still get something that is better than the uniform distribution? Suppose I did not say, as Mr. Fozan asked you about it before. Suppose it's not 10%.
whatever you can set beta equal to 2.2, 0.3, whatever the value here. So it is not necessarily to have it 10 intervals or whatever. This is beta. Of course, you can definitely you can implement uniform distribution. Okay, and you can let us say, even you calculate sigma, whatever the value is sigma, you can go from -4 مثلا to 4, but uniform distribution. Any value between -4 to 4 with the uniform distribution, that's fine, no problem. You can implement it, but definitely with the Gaussian distribution, this is like something will focus more for the good solutions. You focus more on the within or in the neighborhood of this solution. But definitely you can implement it, no problem.
Very clear. Thank you very much, doctor. Thank you.
Okay, so this is sigma, and this is the using the above perturbation, the offspring xn plus I can be determined as follows. X26 equal to x1 plus random numbers that you have it here. Of course, this is a vector. You add this to k, and you add this to t1, and this up to the number of the optimized parameters. So you can have the perturbations here, and you add to the old or to the parent solution, which is xi, to create x26. And of course, this is repeated to 27, 28 until you complete the population of 50. So if any optimized parameter violates its specified range, its value will be set at the appropriate limit. And this is very clear now. You have to stick with the feasible solutions. The generated offspring along with the parents constitute the current population with 2n individuals now. Now we complete the population. And of course, once you have the 26, 27 up to 50, you can calculate their objective functions, these 25 solutions again. And then you can, complete now the first generation of 50 solutions. Now you can do some statistics. You can go and look again for J minimum. And again, you have now 25 solutions more. So maybe one child will, beat his parent, and then you can get a new value of J minimum. And the maximum objective also you need it for calculation of the standard deviation. And the average value, J average, you can combine all the objectives over the number of solutions, which is 50. Then you can get the average value here. So this average value can be used later on in stopping criteria. And if you can have the minimum value is very close to average, all the solutions are very close to the one objective value, you can stop the search based on this. Later we will discuss this, but what is needed is the J minimum and J maximum. Of course, you compare this J minimum with the old value, and you can update the best solution if needed. If this is better than the old, then you can copy the solution and update it as a best solution. So this is what the ultimate objective that we need. Whenever we have a better solution, we have to pick it and store it there in the best solution. So okay, so of course this is updating the best solution. This is what we do. If J minimum is greater than J best, J best is set here at the beginning. In the initial population, we have a J best and we have an X best. Now we have 25 solutions more, so we can compare the objectives. If J minimum come here is greater than J best, معناها ايه? What does it mean? J minimum is greater than J best. معناها انه we have better solution than the best stored or not.
Yeah, this is the best. We can select.
This is a minimization problem, and without loss of generality. We assume انه problem is minimization problem. And all what we are doing here, assuming that this is a minimization problem. حتى the default value for genetic algorithm, MATLAB toolbox is the minimization. Okay, if you need, of course, maximization, you have to, you know how to do it by multiplying the objective by minus sign or whatever. So if J minimum is greater than J best, is this solution better than the best solution that we have so far?
No.
No. So go to step 5 without updating. Don't update the best solution that you store and this solution is worse than what you have now. If not, then you update. Else, update the best solution, X best, and set J best equal to J minimum. You find the solution corresponding to J minimum, and you put it as a K best, X best, and the J minimum equal to J best in this case. And then you can proceed to the next step. So here you don't update the best solution. Now here you update the best solution. Both are going to the next step. Either you update, and here you J minimum greater than J best. If yes, if no, update. Update the best. Is it clear?
If
So
no,
this is how.
if no, should we update or go to 5 right away?
Now this is the here. If J minimum is greater than J best, this is our solution. If J minimum is greater than J best, then if yes, go directly to step 5. This is step 5. This is step 5.
Yeah,
Go
okay, now I
directly to
see.
step 5. If no, that means no, the minimum here is better than the best. This is a minimization problem. If no, update the best solution. And then go to step 5 again also. So this is how the computational flow, flow of this part. Yeah. Is it clear? Any question? Oh, time is over. Let us stop here and continue next class, inshallah.
Doctor,
Yes.
just a quick question here. Now, when we talk about maximization here, are we specifically when we talk about step number 2, which is a mutation? I mean the calculation of sigma here.
Yes.
We should change the J max here to some, or J max will be our.
Again, يا فوزان, you develop your code based on automation. Okay.
Okay.
We will not customize, or for maximization, we will develop a code. Minimization, we have to develop another code. No. Your code or for default minimization. What you can do, you can multiply the objective function by minus sign.
Yeah.
If needed to be maximization, if you need to maximize, for example, in our problem here or in the homework that I gave to you, the objective function is to maximize minimum zeta.
Yeah.
Right?
Yes.
So let us convert it to minimize minus sign here, you multiply it by minus sign. Okay?
Yeah.
Minimum zeta.
Same.
Right?
Yeah.
So in this case, when you calculate your objective function here, your objective function is zeta. You calculate zeta, and you take the minimum zeta and you multiply by minus sign.
Yeah.
Did you get the point?
Yes. Clear.
So this, yeah. So we don't want to go deeply in the code itself and customize it for maximization or minimization. لأنك أنت if you want to implement this for maximization problem, everything will be upside down.
Yeah.
This is built on the minimization problem, where we have if this is a minimum solution, we have very small sigma. If this is the worst solution, then we have very high sigma. But this is not the case if this is maximization. لأن الJ maximum here, if this is a maximization problem, يبقى the one with the maximum value is the best solution.
Yeah.
Am I right?
Yes, that's what.
So the logic will be change. Will change. The logic will change behind this.
Yeah.
Behind this formula.
Yes.
And what you can do is just multiply the objective function by minus sign.
Yeah.
And for this problem, for example, when you have maximize minimum zeta and you multiply here the objective function by minus sign, if you have, for example, your objective function, j or j best here, you will get it minus, for example, 0.5. This is j best from the optimization. And you know, and this objective is multiplied by minus sign.
Yeah.
So that means the actual objective equal to 0.5.
Yeah.
Okay.
Yeah.
So that's all.
Yeah, clear, doctor. Thank you.
Okay. Any other question? If you have question, please. Otherwise, you can leave and enjoy your